Okay, welcome to the second session here of Intro to Data Science or Intro to Data Analysis with R. So in this second session, I'm going to be giving a brief introduction to data. We're going to be looking at how we can import data, different types of data that we can work with in R, different formats, things like that. It's based around, the session is going to be based around chapters 11, 12, and 13 of R for Data Science. I've linked those chapters here at the top of the notebook, so you can see them there. So in this session, we're only going to be scratching the surface of data import, but many of the principles that I'll talk about will translate to many other different forms of data and things like that. We're going to be working with the readr package, which comes in the tidyverse set of packages. So again, at the start of the session, I need to load the tidyverse library so I have it in my environment. All right, so most of readr's functions are concerned with turning flat files into data frames. So there's many different types of functions or many different ways we can import data into our program here with readr. The main ones that I'm going to be talking about is readcsv and readcsv2. So I've got them here on the screen. So read_csv and read_csv2. Most datasets that you'll encounter are stored in and produced as comma-separated values files. We'll get to talking about text datasets and APIs and JSON data in a later session. But for now, most standard data that you'll be working with, you get as a CSV. Now, a CSV allows us to encode rows and columns in our data using comma-separated values. So it's essentially a table that we can work with. So one thing to be aware of is in South Africa, because we use the comma as a decimal place, not the point, not the full stop, if you save a CSV file in, say, Excel, so you open up Excel and you create a CSV file and you save it, it's going to use semicolons instead of commas. So for this, we can use readcsv2. So read_csv is for comma delimited files. So that's any file that you download from the internet where it says it's a CSV, it will be with readcsv. But if it's a file that was either created in South Africa or was created by yourself on a computer that is that has South Africa as its location, you'll need to use readcsv2, and then it reads semicolon delimited files. Great. So with CSV, with readcsv, the first argument is the path to the file. So it's where we can actually find the file on our computer. I'd encourage you to either have your data file right there in the same folder, or to have a folder which is called data, and then within that you could have, say in this case, heights.csv and the various data sets like that. So if I run this command there, it's now gone to the data folder and it's found the heights.csv file and it's imported that in. And here I've given the name heights. So it's taken the table that is in that CSV and put it in this variable here. And we can see up here in my environment that the heights data frame has 1,192 observations. So that's 1,192 rows and 6 variables. So if I click on it, we open it up in a separate tab here. And we can see that this is all the data. I'm not going to scroll through all of it, but there are just under 1,200 rows there, and these 6 columns, these 6 variables in our data set. So let me go back to it there. So this message that got printed out here, because I had message equals true, it's the column specification, and it basically tells me the name of each column. So earn, height, sex, ed, age, race, and so on. As well as then the type, the data type for each column. So double just means that it can hold decimal places. Character is normal characters and things like that. In many cases, you may need to mutate these data types if you want to change it, and we'll talk about that in a second. So for instance, you might want to look at perhaps race or sex or gender or whatever it might be. You might want to change the data type that they are. We'll talk about that. Great. So readr also comes with functions that are useful for writing a CSV back to a file. So for writing CSVs. So if we look at the function here, 2 arguments. So x is the actual data set that you have. So in this case, heights. and then the second argument is the actual file name you want to save it as. So if I run this, it's then going to create in my environment. So if we look down over here, this is my file structure. You can see the other sessions I've got there, heights.csv. It's now created that file in this location. So we can use write_CSV to create CSV files. Something to be aware of is the column type data gets lost with CSVs. CSVs can only tell if a column is a character or is a number. It doesn't have anything else to tell what is the data type of a character. So this makes CSVs a little bit unreliable for sort of caching interim results, so sharing them between files. So oftentimes when I do a data analysis, I might have one RMD, one markdown, which is my data cleaning. And then when I'm done with that, I export a file. And then the next RMD is where I do my actual data analysis. Now, if you are using CSVs to share between these different files, there is the opportunity or the chance of data loss. So then when you read it in, you need to change the column types every single time. So a useful option to store data is R's custom binary format, RDS. Now, RDS is not a good format for data sharing with the public or with collaborators, but it's a good interim data format for sharing from one analysis file to another analysis file. So we can write and read RDS files just as we would with read CSV. So let's look at this example here. So I'm using the pipes from the previous session. I'm taking the heights dataset and then I'm piping it to mutate, and I'm changing the sex column to a factor. Now I'll talk about what factors are in a second, but they're basically categorical variables. So if I run this line, and then I run this line to look at the head, we can see here that height is now, sex is now factor, whereas in the previous example, it was a character. So I've changed the data type. Now, if I read this as a CSV, we can see it's changed it back to character because it doesn't know what the data type is. CSV can't keep track of data types. Here, if I write heights as an RDS, so let me do this where I set it to a factor. Then if I, where did I go here? If I write this to an RDS, we can see that I've got a heights.rds file there. And if I read in the RDS, we can then see that it is a factor. So RDS is useful for preserving data types and things like that. If I want to have it in my environment, I'll need to give it a name. So let's just call this heights2 and then assign that there. So if I run that, we've now got heights2 in our environment, and we can work with that, that data set, that data frame. Great. So before I can go into any kind of calculations or any sort of analysis with our data, remember that figure I showed in the previous session. The first thing we need to do is put our data into the correct format. So we're using this R for Data Science book from Hadley Wickham, and here we're going to be using the tidy format. So the idea here is to take a messy data set and rearrange it into one that is tidy. So I'm going to show you a couple different tables here, and we're going to see different ways of representing the same data. So it's often the case that you can represent the same data set in many different ways. So if we look at these 5 tables, so this is the same data set. We've got different countries. In this case, this is from the Gapminder data, years, cases, populations, similar things here, similar things in this case. This is all the actual same underlying data that is in these 5 tables. There's nothing different in terms of the numbers and values. So each data set is the same set of 4 values for each country, year, population, and cases. But we're organizing them in different ways. And these different ways of organizing the data can either help us with our analyses, or they can get in the way. They can make it more difficult to actually code your analysis. So as I said, they're all representations of the same underlying data, but they're not as equally easy to use. So there's one data set here, the tidy data set, that will work the best with the tidyverse functions. It'll work the best with to be analyzed in R. So we'll take a look at which one that is in a second. So what are the main sort of characteristics here of tidy data? Let me run this figure. So the idea here is with tidy data, each variable must have its own column. So hopefully that makes sense. So that means each column must represent a variable in your data set. Each observation must have its own row. Now we'll see in a second how observation can be a bit ambiguous about what actually is an observation. And then each value must have its own cell. So those are the three rules that define what makes up tidy data. So in the examples that we looked at, only table 1 is tidy data. So if we look at that there, country, year, cases, population. Those are distinct variables. They each have their own column. Each value has a single cell, so there's no multi-values in any one of those cells. And then if you look at the rows, each row is a specific observation. So we've got Afghanistan twice, but in this case, this is the observation for Afghanistan in 1999, the first row, and then in the second row is the observation for Afghanistan in the year 2000. So that's an entirely different observation. Even though this value is repeated, the actual row is a unique row, a unique observation in the data. So tidy data makes it easier to work with because we've got some consistent way of referring to the variables. We know that every column name is a variable and there's not going to be other things in it. And we know that every row in our data set is an observation. The data is then much easier to manipulate, much easier to visualize, and much easier to pipe into models and perform some very sophisticated analyses. So the whole idea here with these tidyverse packages is to have a standard format for the data and then a standard format for how the functions can work with the data. So we can chain them all together in these pipes to, with relative ease, go from a messy data set to a tidy data set to extracting what we need to visualizing right through to modeling and machine learning and all of that kind of stuff relatively easy. Great. So some other things about data sets. So tabular data can be arranged in different ways. So if we look at these two data sets, they represent the same underlying data. We've got the first one and the second one. Each data set here displays information about heart rates observed in individuals across 3 different time periods. So in this data set, we've got Wilbur, Petunia, and Gregory, 3 different times at which we measured their heart rate. So that's the one format. And then the other format here, we've got another way, same data, time, heart rate, and name. So which of these two do you think is in the tidy format? So remember the characteristics of tidy data. We need variables, observations, and then cells. So here we've got name, time, and heart rate. And then here we've got name, but then we've got 3 columns for time 1, time 2, and time 3. It's not obvious necessarily what is in these cells. We don't know that that represents the heart rate measure at time 1, heart rate measure at time 2, and the heart rate measure at time 3. So this data set is not tidy. This is what we consider a wide data set. The values are spread across multiple columns. So heart rate is in 3 different columns. Whereas if you go to this data set, this is in what we call the long format. So wide, it's got more columns and less rows. It's not tidy. Here we've got, it's longer because there's much more rows. So every name here might be repeated, but this is a unique observation because Wilbur at time 1 has a value of 67, whereas Wilbur at time 2 has a value of 56. And if you look, each column here now represents a value. So heart rate, time, and name. So we can easily manipulate those. And when we start talking about data visualization in upcoming sessions, you'll see how having these unique columns for your values can make it really easy to make some quite advanced data visualizations. So we refer to these as the wide and the long formats. I hope you can see why. Long is longer this way and wide is wider that way. So you, for the wide format, each row is often a site or a subject or a patient or a participant, and you've got multiple observations for each variable. So that's often very useful for collecting data like that. But when we want to pipe it into a data analysis, it's much easier to have it in the long format. So we'll talk about how we can get between these in a second. So the principles of tidy data might seem obvious here, that we want our data set like this. But in the real world, outside with real world data sets, it's not often the case that you get tidy data. So there's often a process where we need to tidy up our data to get it into the right format. So the first step is always figuring out what variables and observations are in my data set. Is it in the wide format? Is it in a long format? Or is it in some sort of in-between medium format between the two? And what do I need to get my data to be tidy before I can go about doing any grouping or filtering or summarizing and things like that? So you need to look for where the variables are in your data sets. So let's take a look at a long data set and see how we can go about making it into the right format. So if we look at this data set here, let's make it visible. So a common problem is that is a data set where some of the column names are not names of variables, but they're actually values of a variable. So if we look here at table 4a, we've got these three countries, and we've got column for 99 and 2000. These column names are not actually variables we care about. We don't care about the variable 1999 and the variable 2000. We have a variable year, and these are values for that year. So the value is 99 and the value is 2000. And these values here represent cases of that year. So we actually are showing two observations in one cell. And remember, with tidy data, we only want to have a single observation in a row and a single value in a given cell. So we need to tweak that to deal with that. So to tidy a data set like this, we need to pivot it. So we take the offending columns, in this case 99 and 2000, and we create a new pair of variables to pivot them there. So to describe this operation, I'll show you the code in a second here. We need three pieces of information, three parameters. So we need the set of columns whose names are values, not variables. So in this case, that's this column, 99, and this column, 2000. Then we need the name of the variable to move those columns to. So in this case, we want to create a new column and we want to call it year. And then we need the name of the variable to move the column values to. So that's the 745 and these numbers here. And in this case, we'll call that cases. So that's the number of cases in a given year. So we can take these three pieces of information and we can call the function pivot longer. So that's what I'm doing here. I'm taking my table 4a, my data set, I'm piping it to pivot longer, and I'm using so the C there stands for combine. So what that means is I'm taking column 1 and column 2, and I'm saying take both of those. And we can add 2, 3, 4, 5 different columns there. The reason why these columns are in backticks is R doesn't work nicely with column names that are numbers, so I need to include them in the backticks to indicate that they are not numbers, they're actually column names. So it's taking those two columns, and then it's going to give the names to year, so 1999 and 2000, and then it's going to give the values to the cases column. So let's run this, and we'll see what we have here. So we've gone from country, which we still have there, we've removed 1999 and 2000, and we now have a column year with those values, and then cases has the various values that were in the cells here. I hope you can see that this is a easier format to work with your data in this way, and it's relatively straightforward to pivot longer if you need to. So this in essence is what we're doing. We're taking 1999 and 2000, and we're pivoting the data into this new structure like that. So it's a little bit difficult to get your head around, but that's what we're doing there. We can also do it the other way. So pivot wider is the opposite of pivot longer, and you use it when an observation is scattered across many multiple rows. So here, this is table 2. So if we look here, an observation is a country, and an observation, is a country in a year. So Afghanistan, 1999. But if we look here, Afghanistan 1999 appears in 2 rows, and Brazil 99. Every row country combination is repeated because we've got cases and population. So there's something going on here that we need to make this data set wider. So to tidy this up, we must first analyze the representation in a similar way to pivot longer. So we want to look at what's going on in our data set and how can we deal with that there. So we need to identify what actually is an observation in our data set. Is it a country? Is it a year? Or is it the combination of the two? In this case, we can see it's the combination of the two, but we need to deal with this repetitive structure there. So we only need two parameters. We need to know the column to take variable names from. So in this case, it's type, because those are variable names. We want to turn cases into a column, and we want to turn population into a column. And then you need to know the column to take the values from. In this case, it's count. So these need to become the values of the cases variable and the population variable, and that will sort out these repeating rows there. So same structure. So for pivot wider, we take our data set, in this case table 2, we pipe it to pivot wider. We say names from is type, so it takes the column names from type, and values from is count, so it takes the count values there, and if we run this, you'll see what we get there. So now we've got 4 variables, and each row is now an observation. We don't have Afghanistan 99 repeating or Brazil 1999 repeating. They only appear once. With all of these examples, just as a reminder here, I'm just running these to display it. If I wanted to save the output of this to a variable in my environment, I would need to give it a name and take this pipe and assign the entire output of the pipe to that variable name. So if I run this, you'll see that we have a table new up here in my environment, in my data sets. And just this is a figure here of what we're doing with pivot wider. So we're splitting those values into the different columns there. All right, so far we've looked how we can tidy up table 2, and we've looked how we can tidy up table 4, but we haven't looked at table 3 that I showed you. So just as a reminder, this is what table 3 looks like. So here, in table 3, there's a different problem to table 4 and table 2. We've got one column, rate, but if you look at it, it looks like it's containing 2 variables. It's containing cases and population. So the rate of cases per whatever it is. So in this case, there were 745 cases per, 19 million people, or whatever the case was in Afghanistan. So rate is encoding 2 pieces of information. Now we want to separate those into their own columns. We need a variable for cases, and we need a variable for population. We don't want to have a single variable here for rate. So to fix this, we need to separate it. So if we look at this figure here, we can see that separate is basically taking the first part of a cell and putting it into one column, and taking the second part into another column. So separate essentially pulls apart a column into multiple columns. And we can specify where the separator character is, so where the separation takes place. All right, so let's take a look at the function that I have here. So the function takes the name of the column to separate, and then the names of the columns to separate into. So here I'm saying take table 3, pipe it to the separate function, and I'm saying look at the rate column, and then the second argument is into, and I say split that into cases and population. Remember, in R we use C for combine whenever we want to create a variable that has refers to multiple things. So if we run this here, you'll see what we've done. We've split rate, and now we no longer have a variable rate. We've now got 2 variables, cases and population. So what I think you should notice here, though, is I haven't told it to separate based on the backslash. How does it know what is the separator character? So by default, separate, if I don't specify a separator, it will split the values whenever it sees a non-alphanumeric character. So in this case, it's the backslash. So it goes through, it goes 745, and then it hits the backslash. That's a non-alphanumeric character. So then everything that follows that is going to be in the second column. So we separate it out like that. So that's what it does there. We can specify the separator. So if we look at the second example, I'm taking table 3, piping it to separate. I'm saying take the rate column, split it into the cases and population column, and use this as the separator. So whenever you encounter that specific variable, that's what I want you to separate. So it'll achieve the same thing. And obviously, if your data set has full stops or underscores, you can specify all of those there, and you can specify multiple 3, 4, 5 columns if you need to, depending on the data set. So as you'd expect, unite is the inverse of separate. So it combines multiple columns together into a single column. You'll need it far less than you'll need separate. It's not often that you want to combine columns like this with unite. So if you happen to have, say, century and year, for whatever reason, you could combine them like that. But it's not a common function that you'll need as much. So something to be aware of here is when we're changing the representation of our data, so when we're pivoting from long to wide or from wide to long, or when we're separating values out, it brings up this issue of missing values. I spoke about that a little bit in the first session, but it's worth thinking a little bit more about missing values. So there's actually two ways that a value can be missing in a data set. So it can either be explicitly missing, and what R will do is it will actually flag it with an NA. So in the cell, there'll be an NA, so we know it's missing. But what's more of an issue is when it's implicitly missing. So it's simply not present in the data, and we don't necessarily know that it's not present in the data. So let's look at an example here. So I'm creating a tibble called stocks. It's got 3 columns, year, quarter, and return. So let me run this, and we can then work with that. So there are 2 missing values in this data set. The return for the 4th quarter of 2015 is explicitly missing. So if we see that there's an NA. So for whatever reason, they didn't record data in that quarter, and we know that because there's an NA in that cell. So the column will have an NA in that position. But what's not so obvious is that the return for the 1st quarter of 2016 is missing. So if we see there, we've got 1, 2, 3, 4. But then there's no 1 value, it's just 2, 3, 4, and there's no return value there. It simply doesn't appear in the data set. It is implicitly missing. And that's obviously far more of an issue, because that's going to mess up the values of your data. You're not going to know that it's necessarily not there. So sort of to abstract this, a explicit missing value is the presence of an absence, but an implicit missing value is the absence of a presence. So it's worth just thinking about that there. So the way a data set is represented, so whether it's wide or whether it's long, can help make implicit values more explicit. So it can help us see that they're not actually there. So for example, if we look at this code here, we can make implicit missing values explicit by putting years into columns. So let's run this and you'll see. So now if I put year as column, we can see that there is no value there and no value there. If this was a long data set, we wouldn't necessarily see this. So because these explicit missing values may not be important in other representations of the data, we can set values drop NA to be true. So here, I'm taking the data set, I'm pivoting it wider, so we'll get this, but now I'm actually going to pivot it back to be longer. I'm saying these are the columns, take them, put them into the name, put the values, so these numbers here, into the return column, so that's the return in that quarter, but then drop NAs. So if we run this, you'll see that now we don't have any NAs, it's now implicit. So you have to look at the data set to see that in the 4th quarter of 2015, there is no value. We don't have it there. It depends on the analysis that you're actually going to be doing, whether you need to have NAs implicit or explicit. But it is worth being aware that in the wide format, you'll often see them, but in the long format, you often don't see them. And it depends on your analysis, but it is worth being aware of, are there missing values in my data set, and what's the impact of that going to be on my analysis? All right, so for this last little bit, I want to talk about relational data. It's rare in my experience, but it also depends on what type of data analysis that you're doing, that you'll only use a single table of data. If you're analyzing things like surveys that you export from a survey platform, you might get a single CSV that contains everything. But in many cases, you have data sets that you want to combine together. So you've got many different tables of data or many different CSVs from different sources, and you must combine them together to answer the question that you're interested in. So I might want to know something about spread of diseases in South Africa, and I have years, and I have number of diseases, but then I have another data set where I have years and I have population. I might need to combine them to know about rates per population, things like that. So the main principle here with relational data in R is that each table that you have needs to be structured around the same observational unit. Why is that important? Well, let's look at the following data set and see. So this is a messy data set. So we've got one table. We think it's going to be neater to do this in one table. So we've got data on counties and states and county populations and state populations and different regions. But there's lots of messy data, and it's difficult to even understand what is going on here. So for instance, how can the population for the state of New York have 43 million for one county, but it's missing for another county? There's no value there. If this data set is about counties, what does it mean when the county field itself is missing? What's going on there? If region is, say, for instance, like census region or something like that, how can two counties in the same state be in different regions? It's not clear what is going on in this data set. And why is it that all of these codes for counties start with 36? They're all in New York, but then we've got one that starts with 36, but it's not in New York. How can the states be unknown? So this is a messy data set. We don't know what is going on here. So every table needs to be about the same observational unit. Now, if we run these two tables, hopefully we can see that this is a bit easier. So if we follow the principles of relational data, each type of observational unit should get its own table. So here we have the counties table, where we have the county code, the state, and the county population. Here we have the states table, where we have the state code, the state population, and then the region that it's in. No missing data, no weird values. This is the same data set, just represented as two tables instead of one. So county population is a property of county, so it lives in the county table. So there won't be missing values there. Now all the ambiguity is gone. But what happens if I need to perform analyses that requires information about the county population and information about the state population? So I need these two tables to be separate for my data to be tidy, but for my question, I need to have data from both of them. So for that, we can connect them together using this idea of keys. There's two types of keys, primary keys and foreign keys. Essentially, if we look here, so if we look at the two tables, which value is in common? County, county pop, state, or state, state pop, and region? It's state in this case. So we know, for instance, that this state, New York, has that code, and this county has this code here, state. So we can join in this way. So for every state, there are many counties. So we've got a one-to-many relationship going on here. The primary key is in the one side here, and then it appears as a foreign key here in the many side. So we can use these keys to link up our tables. So we use different types of keys to join our tables together to produce a single data frame when we need it for an analysis. So you should try to keep your data tables separate as far into your analysis pipeline as possible, and then only join them up when you need to. So there's lots of different options for joining, but these are the main ones. So you've got an inner join, and that keeps observations that appear in both tables. You've got a left join. It keeps all observations in the X table, so X and Y. It keeps all observations in the first table. So you could say states, left join counties, and it'll keep every row in states, but only the matching rows in counties. Right join is the opposite, and then full join is all observations in X and in Y. So it's the same thing as an inner join. What's most common here in R in tidy data analysis is using a left join. So in this case, what I'm doing is I'm taking the counties data set, I'm piping it to left join, with state. So that's going to keep every row in counties, and it's only going to match up the matching rows in states. And then the output of this, I'm going to assign to the variable county states, and we can print that out there. So you can see for every row in county, we looked for a matching state and matched it up. So that's the common way we do this here in R. We use left joins to bring in extra information and build it up like that. So that worked because I said by state, and both tables had the state variable. So it knew how to do that. But in many cases, you can use other values to join up your tables. In many cases, they don't have the same column name. So for that, you need to actually specify what the key is. So for example, we've got our Gapminder data here, and we're going to then work with a political data set, and we're going to bring in information from both data sets in order to analyze what we need to do. So I'm going to read it in with read.csv, read it in there. This is just a different way of reading CSV. Let me actually just change that, read_CSV. And now we have both of these data sets in our environment. And this shows us here that that's the columns we've read in. And if we look at the first 6 rows for polity, we have the name of the country, we have the year, and then this is the, it's a level descriptor of something that's going on in the country in that year. So let's read them both in. So we've got Gapminder, we can left join it to polity, and we can run it, and let's see what we have. So it looked at these two different things and said, what is the common, what is the key? What is the observation? And if we look here, it said an observation is the combination of country and year. Because if we just know country, that doesn't tell us anything unique because the country appears multiple times. If we just know year, the year 1800 will appear for every single country. So it's that combination. So it can automatically figure out what it needs to do. And we've now added that variable here to our data set. We've added it onto the end. That's what left join does. So now I'm going to read in another data set. And this is the CIRI data set, and we'll see how we can join that. So if you look again, we've got country, but it's not spelled the same. CTRY. We don't know that that's necessarily country. R doesn't know anything about it. Year, and then physint, a variable that we care about, some characteristic of a country in that year. So for left joins, what we can do is we can, let me just move that up. We can say take gap1 and then pipe it to left join. First, then join it with a SIRI data set, and then by is we can say where country is equal to CTRY and where year is equal to capital year. So R is case sensitive. So we can say where this variable is equal to that variable and this variable is equal to that variable, that's where you join them up. And then if you see here, what we have is we've then added that variable to the end. It doesn't appear for that year for Afghanistan, but if you look here with tail, so head, first 6 rows, tail, last 6 rows, we can see we have values for the year 1982 for Zimbabwe and so on. There's just no values for Afghanistan in those years. Great, so I think that's where I'll leave you. I went through quite a lot in this session. The main important things is knowing how to read data into your environment. So reading CSV like that, or read CSV2 if you need to, and working out in my data set, what is a variable, what is an observation, and what are the values. In the ideal world, you'll get a data set like this, and you won't have to do anything. But you need to be prepared to be able to either pivot longer or pivot wider or separate values out so you can get your data set into the format that you need for your analysis. If you want to read up more on these different techniques and these data types, you've got chapters 11, 12, and 13 here. I've linked them in the notebook. That's of R for Data Science by Hadley Wickham. Great, thanks. I'll see you in the next session.